So welcome back. We have a fantastic seminar today. I just want to remind you guys before I introduce Dan of two now well-known ground rules. Everybody should turn their videos off, please, so as not to distract the speaker, and also go on mute. Please do type your questions into the chat. And Dan, I will try to kind of mediate the questions for you and bring ones that are sort of timely and essential during your talk. I'll try to interrupt you. And then if we could save a little bit at the end to go through some more discussion-oriented questions, that would be great. So welcome, everybody. It's great to have Dan Rock here from Wharton. Former student at MIT Sloan, one of the best students we've ever had. And he is just doing some fantastic work on the digital economy in general, jobs, skills, and various other AI-related topics. And I am really excited to hear about this, what has been called work to vec and sometimes job to vec, trying to understand the structure of the digital economy. So with that, Dan, I will let you take it away, and it's good to see you.
Yeah, it's great to see everyone. It's very thanks for the kind intro, and thanks everyone for letting me come back to give this talk. This is, I know, one of the best groups, if not the best group in the world, for presenting this kind of stuff and getting feedback. So this is work with other familiar folks, and it's great to see a lot of familiar faces here. With Sarah, Eric, and Seb. Kind of the big. All right, so a few things. I have you guys can't see this, but I have a 49-inch monitor here. So this is really great, by the way, if you're teaching and you need to look up something on Wikipedia that you don't know. You can seem like you have all of it at your fingertips, but yeah, if you want to interrupt, I can see the chat and everything too. So I'll pull that up as we go and try and monitor that stuff. But okay, so to get into the content of what we're doing, am I sharing my screen properly? That's the first part.
Not yet.
Okay, here we go. All right, so that changes my chat access, but I'll fix that.
I'll monitor for you. It's fine.
Cool. All right. So we started thinking about this problem as another high-level problem, which was how can we understand occupational dynamism? So over the last, 30, 40 years, the type of work that people do broadly throughout the economy has transformed at a fairly rapid clip. And that means a couple things. One, if we're talking about automation, which is a topic near and dear to this group's heart. For example, in gross terms, if we're creating new work at a rate that's much faster than the rate at which we're automating, then these stories about all the work going away, kind of this Keynes economic policy, prospects for our grandchildren story, we don't have that lump of labor if we're creating a ton of new work. So that's one way of looking at automation, in which case we want to shift our focus to distributional effects of these changes. But that kind of automation story isn't necessarily limited to just machines. It can tell a story about globalization or shifting consumption, where we have a different set of goods and services we buy, or of course, recently something recently now, it's kind of sad, it's been going on for years, but the pandemic has obviously changed the structure of work. So what this paper will do is put into geometric terms how we can understand what the overall labor market is doing and what certain jobs are doing relative to each other. I'll say that there are firm level extensions to this that we're thinking about for the next paper. This is sort of a big fixed cost project that we're hoping will lead to many others. But the basic idea is to build effectively a monitoring tool where we can take all of the online job postings that we have, from Burning Glass in this case, but there's other sources like LinkUp and perhaps LinkedIn if you're working with them, and boil that down into something that describes the labor market in general. And there's a few ways of doing that. There's a few different types of models that we train. Sometimes we're going to be making kind of this big multi-dimensional, manifold space, whatever you want to call it, sometimes we're going to be trying to hop around in that space and understand what those moves mean in interpretable terms. So if you want to keep one question in your mind while we're talking about this stuff, like what's the empirical thing we try to figure out? That question is going to be, what's the rate of creation of new work? And I'll get into why that's important. But it's a measurement of something that we haven't really been able to do before. The answer is, as Sarah likes to say, has been hiding in plain sight with all these postings, but it's really only, recent advances in AI and, well, it's AI in PowerPoint. I'm in PowerPoint now, and machine learning when you actually build these things. With apologies to the good old fashioned AI fans in the room, but it's only these recent advances in ML that, and particularly text processing, that let us get at some of these measures. So some of these motivational ideas will be highly familiar to all of you, but we care a lot about what happens to displaced workers. So when you have something bad happen to you at your job, whether that's getting fired or automated, or maybe your company goes bust, these people experience long-lasting damage to their careers, their earnings, all that stuff. So if we can monitor what's going on in the labor market by looking at job postings or looking at sort of stocks and flows, different types of work in a different way, we can understand like where's that stuff happening, where's there kind of negative shocks that you want to avoid, where are there positive shocks that you might want to move towards. So that real-time measurement can help people make better career decisions. Sarah Bana, her job market paper has got some great additional uses of models of this type, trying to predict, say, the value of a credential, or help people understand trade-offs associated with different major choices. For example, you can use this kind of tool for that. So there's many different things that you can do with this kind of data, this kind of model. To some extent, people will see whatever it is that they're most excited about in these kinds of tools, and that's great. We're really excited about that. We're going to try to provide a few of those different examples of things you can do with this, with kind of a coherent picture of which jobs are changing a lot, which jobs aren't. So 2 goals. I'm going to talk about what our early results look like and some of the different facts that we found. But then also, I want to emphasize that these methods are highly flexible. We kind of think of this as, if you were around running regressions by hand, decades ago, and that was sort of limited to a small subset of people who actually ran regressions. But then obviously linear regressions, that is, have proliferated into the rest of the research community. We kind of think we're at that sort of moment for a lot of these ML techniques where we're early in the proliferation cycle, but it's been, these techniques have been opened up to people like us. We're not computer science experts. We're not the sorts of people that would write millions of lines of code to get a neural network stack running. You can do this in TensorFlow. I've got some papers on that too. You can do this in PyTorch. These things have been opened up. So huge opportunities to deploy these methods for traditional questions, even like what's automation doing in our economy, right? So how do we measure this stuff today? Well, we took inspiration from this paper by my colleague here, Sunny Tambay, Dokyun Lee at BU, and Jiaoqi Chang at CMU. So they looked at the creativity literature, and they were thinking about patents. So when it comes to patent innovation, there's a few different ways you can create innovation. One is to take 2 existing ideas and recombine them. So think of that as like a linear combination of 2 ideas, and somewhere in the middle, those combinations of ideas hadn't been tried. So that's one kind of innovation. Another kind would be to look at the full space of all the different innovative ideas and push that space out a little bit. I mean, maybe some of you have seen that, what's a PhD? It's like there's this frontier, and then there's like this little bump on the frontier and an arrow, and it's like, that's my PhD. That's kind of your expansion of the frontier, expansion of the creative space, kind of creativity. So Sunny and his co-authors, and Sunny DK and Jiaoqi, they have another one, which is transformative creativity, where you kind of bounce off the page in a way. You create a new dimension for innovation. I would argue that's a little bit like frontier expansion. We're going to leave that one aside for a second and look mostly, are we destroying old work styles? Are we expanding the job frontier? And are we recombining existing roles? And importantly, when you expand the frontier, as there's this Weitzman paper, I'm forgetting the exact reference, but if you expand the frontier, you create, exponentially more combinations within the space. Whereas if you recombine them, that's more of a linear increase. So, recombining possibilities on the margin should be roughly equivalent to the returns to expanding the frontier. We're not going to get into those returns or any theory things, but that's for those of you who are so inclined, something.
Well, I mean, just not to nitpick, but that seems
Yeah.
like a two-dimensional thought process in terms of what you just said, in terms of recombination, right?
Right. Even in multiple dimensions, right? So say you've got 3, 4, and as it turns out in our models, it's about 30. If you were to recombine something, there's only so many, like as opposed to creating a wider, if your whole space gets bigger, now everything can be recombined with all of the stuff that expanded along the frontier, as opposed to if you have just a line or a plane connecting a couple points, there's
Yeah, I'm thinking about the case in which recombination uh, is also expansion, right? It
Oh,
creates.
sure. Yeah. That, think of that as your weights for a convex combination. One of them is outside the thing. Absolutely. That's a perfectly, that's compatible with what we're doing here. So, kind of build on that. What we're going to do here is take that text that we don't have any trouble interpreting what the text means, but we do have problems doing geometry on text. And let's see if we can kind of measure how quickly the universe of jobs is expanding. So we're going to try to identify, if there's planet software engineer and planet salesperson and, another one for technicians or something. How far away are those places? Are they moving away from each other? Are the planets getting bigger? Is there more, are they actually little galaxies, that kind of thing? That kind of spatial representation, that's maybe a good analogy to keep in mind. Though, of course, if you have better ideas for how we can explain it, I'm definitely all ears there. So our baseline model here is going to be BERT. We think BERT does the job reasonably well, and it's sort of like the simplest of this family of language models, large language models. You can do this with GPT-2 or GPT-J. We're actually building that right now. We've got a compute grant that expires soon, so we're trying to set as much of the rainforest on fire, building these new models as possible. Actually, since we're doing transfer learning here officially, it's actually not that bad. But yeah, the approach is modular. You can swap out a lot of these things and build a new one. The types of models we're going to train, first, what we're going to do is something that's like, I would say, practically useful from an engineering perspective, but not super interesting from a research perspective. And that's taking the text in, chugging it through this model, and having it predict one of 824 ONET categories. So for those of you who aren't familiar, ONET's the government's taxonomy of different types of jobs. It's saying this is a software engineer, this is a technician or something. So that's a problem a lot of businesses face. How do we classify jobs? We'll open source this model eventually, and hopefully people can use it. But the first objective is, can we do this multiple classification problem? I will say the importance there, we can look at accuracy as a diagnostic, but it's not super useful for anything. What's useful is to look at where you screw up, because that will tell you, did the model learn structure? If we screw up with a salesperson and we land nearby at sales manager, right? That's not a bad thing. That means that the weights inside the model have learned some sort of latent representation of the job, similarities. But if you screw up by saying, oh, it's a nurse, well, now we're just defaulting to what's likely prior. So I'll talk a little bit more about that. The next thing we're going to do is invent a couple new approaches. So we call this text injection. A lot of the time, it's really difficult to express an idea in numbers such that we can measure it. Operationalizing stuff, and for those of you reviewing papers, right? Like That's always a big question. How did you operationalize this idea? Well, what's nice is we can automatically operationalize ideas with this. So if I write in, and I'll show you this soon, the ideal candidate for this position will work remotely. I clip out part of a job posting and stick that into the job posting instead. And I'm going to reclassify that posting with my modest, little change. If I shift towards certain types of work, averaging over many postings where I do the same thing, and shift away from other types of work where I, do the same kind of exercise, what I get then is a ranking of different jobs based on how likely they were to contain remote language. So the kind of exercise that Dingle and Neiman did, trying to predict which jobs are remotable, we automate that with this kind of thing. So that's kind of like hopping around on this big space. And then another thing we'll do is kind of an unsupervised exercise where we're trying to learn the structure of this clustering. And with that, we can do some interesting things with geometry. Yeah, Hangi, what's going on?
So I had a quick question about the text injection, which is like, how do you decide where to hop around? Because you do have the entire space of the dictionary to choose how to inject. Is that sort of like something that you came up with an interesting list of words to try out, or was there a more systematic way of doing
I will get into that in, I don't know, about 20 minutes or so.
Perfect.
Dan, David Eddy asks, what about tech jargon? How does this this model or this process handle sort of like tech jargon that may not be as amenable to NLP methods?
So tech jargon is really useful, actually. If you have weird names for skills and technologies and things, then we get really clean cuts into what the effects will be. Where you're more likely to run into trouble is sort of that latent stuff, where we over time start to expect that people know how to use Microsoft Word and stop asking for it in job postings. So that latter thing is more of a worry. If you're saying, I want someone who knows TensorFlow, well, TensorFlow is a weird name. We can pick that up, and I'll show you some of that too. But that's a great question. All right, so some quick headline things. What do we see? Well, from 2010 to 2019, where we have data, the job space is almost like monotonically expanding, which is interesting. We don't see much destruction of the previous job types. So there's maybe a little bit here and there, but that kind of keeps with this is in gross terms, right? If someone's doing this type of work in 2010 somewhere, they're probably doing it somewhere in 2019 as well. Maybe it's just too short a period. And that said, there's a lot of roiling heterogeneity underneath the surface.
Does that account for sort of like the weight of the number of mentions, or is it just does
No. Yeah. So there are definitely some jobs that are declining in how many people are doing them. But the wholesale elimination of that work. So there's certain parts of there are certain parts of the space that are more densely populated.
And to what extent are we worried about the representation in job postings being about empty positions rather than positions that make up a bulk of the economy but don't require more hiring? So for example, let's say that I have a job category that's a very major source of or major space in the labor market, but it's actually shrinking. So nobody's hiring, so there's zero job postings of that, but plenty of people doing that work.
Yeah, that's the sort of thing we'd pick up where as there aren't very many people doing that job, you'd see or asking for that job, you'd see a collapse in, say, even the diversity of ways that people ask for that work. And then actually for that question, I would say you don't need any of this infrastructure. Just look at how many people are being hired into those occupations, and then we can tell this is someone we have to care about. But that gets exactly the distributional point that we want to emphasize. There's some jobs that are doing better off, or that are better off than others. We have a few diagnostics to figure out, what's going on. Is that an answer to that question?
Yeah.
Okay, cool. So I won't talk about this for too long, but this is, I think, a great kind of story that illustrates how this might have gone a long time ago. So there's this really nice paper by Feigenbaum and Gross that talks about telephone operator work as it was automated by AT&T from 1920 to 1940. So this was an entry-level job, typically for women in the economy at the time. And they found that, as you rolled out all of this automation, future worker cohorts, they weren't damaged really at all by that. But the people who were in this job when the automation happened, they were negatively impacted. And our question is kind of like, well, this is happening across the economy in lots of different ways. Who are those people, to Sinan's point, like, who are these telephone operators today? What are maybe the adjacent jobs where they might go? So that's another thing you kind of get for free out of these models. These questions, we know lots about technological advances and their potential to shift labor demand in different ways, going back to Otter, Levy, and Murnane, where kind of interest rates do the causal action there, interest rates relative to wages. More recently, sort of this Acemoglu-Restrepo line of research. And then, of course, there are distributional effects. These are kind of nothing, there's nothing surprising here. You can think of this paper as maybe adding a measurement layer to the Acemoglu-Restrepo man versus machine framework that they pose. So we have decent measurements of, automation exposure from 5 or 6 different papers now. In fact, I saw another one today. There are not too many papers. There's one by David Otter and some co-authors on this. Not too many measuring new task creation in sort of an ongoing automatable way. So if we can get at that question of how many new tasks are there, how many new types of work, what's the relative rate of new creation there, that might be a useful thing to do. And Ganadale et al., like they kind of get into this, but they don't quite, they look at things from like a routineness perspective too. All right, so I'm gonna skip over some of this stuff. So preliminaries on the data, we're using Burning Glass. So for those of you familiar, Burning Glass, as they claim, is the near universe of online postings. This is a sample that's a little bit weird relative to the rest of the economy. So we have like many, many more computing, software engineering, those sorts of jobs tend to all be online. We have a lot of truck drivers, a lot of nurses. That stuff's pretty well measured. On the other hand, if it's a construction role, for example, there's some missing data here, and we're going to have to reweight, or we actually changed the sample a little bit to try to incorporate language in general, kind of fine tune things a little bit. It's not explicit fine tuning, but there's a lot of parameters in this model. So, we have more than enough to capture a bunch of that. But like, food prep, construction, some of those in-person jobs that we've seen, even things like movie production, that stuff might not have been represented as well online. I think one of the worst categories, for example, we have is dredge operator. There's like 64 postings throughout the entire sample for that. On the other hand, salespeople, we have a ton. This is, sorry, I got cut off there. This is like the word length of each of the postings, a density plot of that. So most postings tend to be somewhere around 500 words. That's good for us because BERT can only take in 512 tokens. So what we're going to do is clip the postings at 512 at random places. You can actually do some data set augmentation there. And then kind of implicit in postings, because there's a lot of boilerplate language, you get this kind of noise penalization for free, where, if you're talking, it's got the same language, or it's just about the company or something like that. Maybe they've got a really long preamble. That's not going to contain any information about what the job is. So you're effectively throwing noise into the model, and that's going to help prevent overfitting. A lot of these models are really prone to overfitting. Yeah, Hung, you got another question?
So for each sort of training epoch, are you just basically taking one posting and randomly selecting 512 tokens and chunking it up, and then the next epoch you do the same thing, but there's like a different cutoff points, or is only one posting? Is it
so
consistently
it's more like we're going to take random 512 ordered, like you have to preserve the order there so you keep the context. We don't randomize the stuff, but it's more like each cut of the posting represents its own version of the data. And I think actually we have so much data that we end up just taking one cut of every posting for the training. So that doesn't end up, we don't need it.
So that cut remains the same across training epoch. It's not getting recut every time.
Correct. Yeah, but that's one thing we're looking into doing, is like validating on other pieces of the posting. So you can see the sample does move though. I mean, like we're taking these cuts. In 2010, software developers are the most common thing. There are about 480,000 postings there. By 2019, you've got 1.2 and 1.3 million postings for nurses. Salespeople are kind of there the whole time, and now like truck drivers are a big piece of that. So the sample does change. We try to deal with some of that by balancing the panel. Most of the results you'll see are actually on a balanced panel of firm job combinations. So I think we have them with regions that's balanced as well. It doesn't tend to change results too much. So that's good news. Here's how we change the sample. I don't think you want to do that thing that people sometimes recommend where you take all of your different categories and you make sure there's equal amounts in each one of them. That's a little bit of overkill. On the other hand, we don't want something that's just going to guess nurse every single time. So that's going to inhibit our training. So what we do is we look at the 75th percentile. Does it seem like a, as principled a cutoff as we could make? If you have more than the 75th percentile count of postings in a given year, we only take up into that count. So it turns out that number in 2019 is about 27,000. We only sample up to 27,000 postings of a given job type. If you have fewer than 27,000 postings in your job category, we use all of it. Okay, so that's going to help us find a somewhat balanced, or balanced not in the official way you might balance a panel, but a class balanced panel. All right, so a quick thing I want to get into, and then we'll start going through results. You might ask, why don't we use something like TF-IDF or Word2Vec, especially given the name of the paper, instead of BERT, one of these transformer things? Well, it turns out that the context for how words show up is extraordinarily important for understanding, what these words mean, understanding in the sense that the machine might understand them. And postings actually have really similar language, even if the jobs are super different. So on the right-hand side here, we've got a machinist that works at Anheuser-Busch. And on the left-hand side, we've got a senior machine learning scientist at Amazon. And machine obviously means very, very different things to each of these groups, but completing assigned work efficiently and per standard operating procedures, right? Those might be similar words in Word2Vec to using machine techniques. I'm cutting out statistical and learning here on purpose to create scalable, traditional, and non-traditional approaches, whatever that means. So if you don't include the context, you're going to get the wrong answer a lot of the time. Here's like a word cloud for Python in Word2Vec. Python, for those of you who are masochists, by the way, and want to play a harder version of Wordle, Sarah has turned us onto Semantle now, where Semantle tells you how close you are to a word you're guessing, whatever the word you're trying to be. So if you had Python, right, one of the closest words for Python is Monty, right? Or snake is also close. We don't want to be telling people to become comedians. There's already enough of those, right? Like there's Semantle is totally nuts. You either love it or hate it. It scratches some weird itch in some people's brains. So Word2Vec is actually a great model for many use cases. For ours, we're going to lose things if we go to a bag of words approach as opposed to a context-driven one. So BERT's going to give that. I'm going to skip over how BERT does that. The TLDR with our model is we're going to take n postings, which turns out to be a few million in each year at least. They get broken into 512 postings. So that's your matrix of postings by by tokens, 512 tokens. Then we stick that into BERT. And for BERT, each token has a 768 dimensional vector that represents it. So now we've got a tensor that's n by 512 by 768. Now that's going to go through a one-dimensional convolutional layer that's going to kind of move this window along the text and create more features. And then we're going to pull that. We're going to take the max of blocks of these features. So that gives you an n by 64 matrix. You flatten that and batch normalize it. So you take out the mean and divide by the standard deviation within the batch. You stick that through one last sort of logistic regression layer, and you get to 824 classes. So this is like visually what that looks like. We stick it through BERT, we stick it through a convolutional layer, we stick it through a max pooling and flattening layer, you got a logistic regression at the end, boom, you've gone from text to 824 classes. All right, so how do we do? This is just for the prediction thing. Well, our top one accuracy is about 76%. So out of the 824 classes, we get the right answer about 3/4 of the time. And a top 15% accuracy is 95%. So we're learning structure here. We're also using what Burning Glass tells us to be the job category, which isn't necessarily correct. So you don't want to go to 100% accuracy anyway, because it might not be right. We just want to learn that structure. In the meantime, this is useful for whatever you need. There's about 110 million parameters. I'll skip over that. So why do we want to train a classifier? Well, it turns out that beyond doing this prediction while making that available to people, that latent structure, we want to maybe warm start the hundreds of millions of parameters so we can start measuring that space. Okay. The other thing is when you classify these different jobs and you look at like, well, what did we actually classify this job versus that one? You start to get a sense of what this uninterpretable model is actually doing under the hood, and you get a sense of being able to sanity check this thing. All right. So substantively though, unless we know that we're doing reasonably well classifying the jobs, then there's too much noise if we try to compare two classifications. So when we clip out some text, replace it with another, we want to make sure that it's not swamped by that noise. All right. So Sarah uses this for salary stuff too. She is more, if I think of everything in terms of unsupervised learning, Sarah thinks about it more in a supervised way. It's probably more useful for economics to think about things in supervised ways most of the time. All right. So let's talk about this remote work example, but this will work in a general sense for indexing all types of work using postings on kind of new criteria. So we wanted to understand what's the ranking of jobs from most remotable to least remotable. You can go through all the jobs and rank them. There's a good paper that does that, Dingle and Neiman. But what if you just wanted to make something scalable where you can do this quickly and you're not relying on individual judgment? All right, so we're going to do that clipping thing. We stick a concept into some postings and compare them to their counterfactual posting. It's not really counterfactual, but they're different posting had we not but for our change to the posting. All right, so when you put in this is a full-time remote position and employees can be based anywhere in the United States, the occupations you predict towards, this is the diff off the changed posting from an unchanged posting, you shift towards frontline supervisors of office and administrative support workers, computer support specialists, a lot of managers. So the weird one in here was food service manager. I looked up what they do in ONET, and like of their 30 odd tasks they do, maybe like 2 of them are things you have to do in person. And those things could easily be offloaded to someone who's not in a managerial role, like, taking inventory, for example, you kind of have to be in person. Maybe stick a camera there. There are ways around this stuff. On the other hand, the least frequently predicted occupations, we saw a lot of capital intensive work, like, repair people, that kind of stuff. We saw food prep workers, that was the top one. And then a lot of, remote education, at least up until 2020, that wasn't really a thing. And as we've seen, actually teaching remotely, it comes with its own set of trade-offs, especially when you're looking at elementary school kids. It seems like it's much better for them to be in person. I have one person once tell me, truck drivers are not likely to be remote. Someone told me truck drivers are kind of all remote. I thought that was it's an interesting challenge to what I think of as remote work. So we compared this to the Dingle and Neiman stuff. We predicted, across the usual limited dependent variable, binary stuff, different kinds of model specs. Our predictions for, if you regress those Dingle and Neiman scores, which were hand curated on our scores, you get positive and significant correlations. So don't worry about too much the coefficients there. They're all scaled. Comparing that to some of the work that Hong Yi, John, and our co-authors that we've done before, you see this kind of show up as well. These managerial roles tended to switch to remote work at the beginning of the pandemic too. All right, so you're getting into some of those weird words. If you put TensorFlow into a job posting, you start to see a lot more web developers, computer systems analysts, programmers, software engineers, that sort of thing. See a lot fewer parking lot attendants. See fewer mental health counselors. Maybe Google should take that under advisement. If you put R and SQL into a posting, you get more computer information research scientists, data scientists going to live there. Fewer cooks, fewer dining room and cafeteria attendants, that sort of thing. So these are sort of intuitive results. We were excited to see that. It works mathematically. I'll say very little about the proof here. If anyone wants to discuss this offline with me, I'm happy to do it. But the condition you need is that the location you clipped out and the text that you put in, those things are uncorrelated in terms of classification signal. And then you get this log D thing. That's a denominator. This is in the bottom left here of my screen. That's a constant factor that's true for all postings. So if you wanted to know the absolute change, you'd have to estimate that factor. But if you just want to know rankings, that diffs out. All of the postings have that. All right. So I'm going to get into what I'm most excited about with this paper. This classifier is nice, but if we're trying to represent distances between jobs, we want to know how far is planet salesperson from planet, phlebotomist or something. You're effectively trying in high dimensions to put lines or planes between these things to separate them. So, to kind of torture the analogy a little bit farther, if everybody speaks a certain language on a given island, and we just need a little bit of water to separate that island from another one, this model classifying things is going to be indifferent between a lot of water or a little bit of water. So distances don't mean anything. They're contingent on how much we trained. What we want to do instead is regularize those distances, penalize being far away, such that the space kind of gets pulled in and everything's consistent. You want a regular space. For that, the right tool is called a variational autoencoder. This is principal components analysis on steroids. You have two things you're training. One is an encoder and one is a decoder. The encoder takes a vector and represents it. It pushes it through this lower dimensional space so that we represent everything as a lossy compression of whatever the input was. The decoder takes that lossy compression and expands it back to the original space. So by training this thing, what our goal is really to get that set of components on the inside. Now we're going to take that 824 dimensional job vector, just probabilities you belong to each one of these jobs, cram it through a lower dimensional space and try to expand it back out. So the inputs and the outputs are actually the same thing here. And our goal is to get them all. And that's going to give us some way to represent distances between jobs. All right, so basically you're using a multivariate Gaussian prior. I don't have to talk about that too much, but here's visually what the difference in the model is. We've got mostly the same ingredients. We're sticking the job text in, it goes through BERT, goes through the classifier. We get that 824 dimensional vector. Now we're sticking it through this new encoder so that we're trying to get these different factors. We're going to use 30 latent dimensions, but you can use a bunch of different things. This is what we settled on. Yeah, Hangi, go ahead.
So is the goal here then to just try and predict one of those 800 labels using this 30-dimensional vector that you get from the encoder?
Yeah, for the decoder, exactly.
Okay.
Yeah.
Right, I see.
So here's what that looks like if you pick different counts of dimensions. You get a decent job. This is the loss in the classifier, the autoencoder on the y-axis. Here's our training epochs on the x-axis. So as you train, you do reasonably well with 5. You do a lot better with 10. By the time you've gotten up to 45 down there at the bottom, the differences are not that much. So we picked 30. You can use the elbow method here with the final set of loss, which is scientific lipstick on an artistic pig, I guess, where somewhere around 30 dimensions we got this bend. Our loss isn't going down as much, so the first derivative kind of levels off. That's why we picked 30. Okay, here's what they look like. There are 30 things. They're Gaussian priors, and they mean different things, but they're kind of difficult to interpret. We can look at a few of them. So this is uninterpretable typically, but what you can do is take, say, 29 of the dimensions and fix those at the mean. So let's take a standard normal. We're going to fix that mean at 0. And then we're going to vary one of the components, the last one we haven't fixed at 0, and go from -3 standard deviations down to 3 standard deviations up and see how that job changes. So it turns out at 0 with everything, just about, logisticians are kind of like your stem cells of all the different jobs. Turns out trying to figure out how to do things, move things around, that's like a general purpose kind of labor. But if you go on our first factor from -3 standard deviations, that's paralegals and legal assistants. As you start to increase that factor, you go through stock clerks, you go to logisticians. By the time you're a standard deviation up, you're at computer and information systems managers. If you really go extreme on that, you end up at architectural and engineering managers. My favorite one of these, in some sense, paralegals and architectural managers are opposites. I like the one that, oral and maxillofacial surgeons are in some ways opposite to missile and air defense crews. So, kind of until I see a dentist using missiles, I'll be okay with our results here. So there's 30 factors here. You can do this kind of exercise. Statisticians were kind of opposites, to those of us who consider ourselves statisticians in some hobby way, like I might. You're kind of an opposite of a purchasing agent or a first line supervisor of housekeeping and janitorial workers on one of these dimensions, right? You see some of these things, they look kind of like outdoor work. Some of them look like indoor knowledge work. They combine in nonlinear ways, but it's sort of strange. You can combine them in linear ways too and get interesting results. We can decompose occupations too. I won't talk too much about this, but you can see even though like the counts of, this is pilots on the left side. So pilots are increasing. There's a lot more pilots in our data set. Nevertheless, the spectrum of all these different factors is relatively stable. It doesn't move around a ton, okay? So that's what you'd expect. Pilots' jobs haven't changed too much. This is sort of like those chromosome plots that you've seen. Office clerks, on the other hand, they've been bouncing around a ton, and there are some factors that are pretty volatile. So, in factor 16, going from social worker to clerk, we've been seeing them move more towards clerk, or down in factor 18, away from CEO and more towards delivery. So there's sort of a de-skilling going on with clerks. You can do this for lots of different types of jobs. And in general, our factor spectrum is declining over time. So, we only have a couple minutes here. I'm gonna skip over some of the stuff. You can do this for firms too, where you aggregate over the different measures for all the jobs at the firm, what they're hiring for, and then you treat the firm like a job and classify it using the decoder. We find that Facebook is, say, a public relations specialist. Many universities are post-secondary school teachers. CVS is a pharmacist. So you can tell here a little bit what Facebook is producing. It might not be code, just a thought there. You can plot these things in different types of embedding. So this is some work that I'm doing with Sunny Tanbay and Barry Wang, one of our PhD students here. I call these Death Star plots. And you can kind of see arranged here around the sphere, different rotations indicate different types, different angles indicate different types of work. The depth into those types of work is like how deep into a cluster you're going. So this is like a continuous hierarchy in a way. On the left-hand side, you see a super complicated company that does everything. On the right-hand side, you see one that's extremely good at sales and marketing and technology. The left-hand side is Walmart. The right-hand side is Google. So interesting kinds of breakdowns. We're working on building some measures to capture some of these ideas. Jobs don't move the same amount. In the interest of time, I'm just gonna, this is fun stuff to talk about, but I do want to get to our bigger picture stuff and take a minute here. So you might ask, what is this overall, to get back to the original question, what is the posting space doing? If it's 30 dimensions, fine. Is it getting bigger, smaller? What does it look like over time? So here's a two-dimensional representation of it. We map these, this is UMAP. In 2010, we have a lot of clustering. There's this big clump of jobs kind of at the center. And that line around the outside, that's the convex hull. Those are our weird jobs. And there's a little bit of filtration of those jobs out towards the weird jobs. As you look at this over time, here's 2015, that clump is starting to expand. There's more jobs close to the weird ones that were on the frontier. As we go to 2019, now the space is really filling in. We've got much bigger, clumps in other spots, even though our core thing is still in the center. So this is qualitatively kind of what's going on. We're seeing some expansion. It turns out if you wanted to calculate the convex hull for all of the jobs all at once, that would never converge. I discovered that the day before I was supposed to give a talk about this. So we invented an algorithm that is sort of inspired by a random forest. where you resample jobs and you build a space off those resample groups. So we maybe get like 10,000 samples of 1,000 jobs. Now we're going to calculate the convex hull on those 30 latent factors, and then we're going to calculate the volume of that hull. Okay, so that's going to be a measure of how big is the job space in some sense. And what we were really surprised to find is that there's not a year in this entire decade where the volume of the hull isn't bigger than the previous year. Okay, so that's what you're seeing in this plot. Rather than comparing means, we're looking for first order stochastic dominance. Is the one graph to the right of the other, kind of representing that as PDFs. The convex hull volume is expanding over time, and it's also becoming much higher variance. So as we're sampling these things, some of the job spaces that we sample have a lot of volume, some of them don't have much volume, which shows, since this like uniformity is kind of, things are becoming less uniform, that frontier is not only expanding, but getting filled in a bit.
Dan, can you just comment briefly about the extent to which this captures the expansion of posted jobs versus jobs, the expansion of people posting online?
Right. That's a great question. So this graph is probably the best answer I have to that, combined with the idea that we're looking at a balanced panel here. So these are all firms that were posting online and adopted online postings from the beginning of the sample. Nevertheless, we see many more postings, bigger counts, right? So you express that maybe as a compression in the variance. I would say up through 2015, there's much more rapid adoption. So you can see that in the graph. This is like the relative, size of the convex hulls as they change over time. By 2015, the growth rates have slowed down a little bit. Nevertheless, you're looking at maybe not 4 to 5% increases per year in the space volume, but maybe 2 to 4% increases. It's still a rapid clip. So if we're going to think about, say, automation and taking away jobs, we've got to be destroying new types of work, or we've got to be destroying work and allocating it to machines at a rate faster than our gross creation of new work. I would say at 2 to 3% a year of creation of new varieties of work. That's not something we should worry about. And that kind of lines up nicely with the fact, I forget the exact statistic, like half of all work didn't exist in like 1970 or something, 40%, something like that. I forget the exact number. But like, if you think about everybody filling into those new types of roles, as opposed to the extensive margin, which is what we're picking up here, creation of new work. Nevertheless, possibly the biggest worry I have about this kind of work is that language has just changed in some way on these online postings. And then maybe it's not representative of jobs overall. I think we can bound that with balanced panel results, but we don't get to a perfect answer there. Yeah, the areas are the same too as volume. So kind of getting back to the big picture.
Daniel.
Yeah. Oh, sorry. Go ahead.
Is there any evidence? Is there any evidence of the job sort of frontier not just expanding but also shifting a little bit, so that parts of the frontier are just getting eaten away?
Yeah. So I skipped over these results just because we only have an hour, and this is and typically I've got about an hour and a half to talk about this. But if we'll go back here quickly. So here's paralegals, for example, right? So on the left-hand side, we're looking at the centroid for all of the jobs that are paralegals and where it went over time. Those are like 95% confidence intervals there too. So the centroid, it moves a good amount, but it's been moving less for paralegals in terms of point estimates. I mean, it's still all within confidence bounds. It's been moving less recently than before. On the other hand, the average distance to the centroid of those roles, that's also been collapsing, right? So what you might interpret this to mean is that paralegals are becoming relatively more standardized in terms of what people ask for. And then to get at Sinan's question, after 2015, as people adopt online postings, that kind of stuff, we would expect to see a little bit more of a stabilization in what people are doing. Maybe it's the weird ones who start asking for paralegals earlier. But the coefficients here, these distances in raw terms, they're not really that big. So it's not that different from what people were doing before. Okay, so if we're thinking about
Dan, a quick clarification question. So your paralegal is represented by a vector of how many dimensions? 30, 80, something, 30. So
Yeah.
can you just quickly, if you got time, just clarify like how to get to 30 in the sense, so with BERT you have a 768, and then you
Right. So that comes from, going back a bit, here, where we were trying to figure out how many dimensions do we want to cram all the postings through. Do we do 5, 10, 15, 20? Turns out the loss is kind of kinked at about 30, where the derivative of the loss starts to go down a lot once you get to 30. So we stop there. It's I would say a principle, but it's not an exact kind of thing.
No, that's fine. But like I'm saying, like, so the question is like, how do you so you're using the autoencoders for some kind of regularization. So
Yeah.
Clustering is like the basic idea, but how do you compute this loss? Like,
Yeah,
you
so
know, you have to predict something to compute this loss, right?
Yeah, the thing that you predict is the same as the thing you put in. That's an autoencoder
Oh, okay.
is cool like that, where you know the ground truth, because the ground truth, it's an identity function to some extent you're trying to learn.
All right. So this is the dimension reduction you're doing using the autoencoders.
Exactly.
All right. Thanks.
Sorry, I should have spent a
No,
little
no,
bit.
thanks. It's clear now.
Yeah. So yeah, we got to this thing where I think, at least in a preliminary way, and we're still kicking the tires on it, of course, we're starting to measure what is the rate of that new task creation, at least on the extensive margin, right? So the intensive margin, you might weight that weight of new task creation by how many people are taking roles there, you know, after the emergence of a new pocket in this space, you know, how long does it take for people to fill it? That's all work to come. We also, of course, being, you know, the sort of econ focused people we're always looking for that next causal step. So to the extent that people have ideas there, we're happy to chat. That'd be really helpful. We were thinking like, you can certainly do shift share stuff. You know, some of the technology skill shocks that John and Sunny have written about, or some of the stuff I've done, we think that might be useful too. So we'll use that to test some more of these theories. Anyway, so that's going to wrap us up. I wanted to point out here that like this is just a first, you know, dip of our toe into the wide world of text processing and what you can do to answer economics questions around it, or IT questions more specifically, as we've seen with some of these tech skills. We were kind of interested to find out that, yeah, it looks like the occupational frontier is expanding, at least over the last decade. It'd be really interesting to know what's been going on for longer than that. So we're excited to get every year another set of postings. But you know, this is a great area and a fruitful area we find for investigating all sorts of new questions. So we should have a draft really soon. We have an old draft that's kind of differently focused, and we're doing that usual overhaul kind of stuff. But you know, if you email me, I'm happy to share that with you as soon as it's available. In general, comments and suggestions always welcome. And thank you very much for your attention. I'm grateful for the chance to get to present here.
Thanks, Dan. This was great. I got a number of messages saying people would have listened to this for longer. Really, really interesting. Really excited to see how this work develops, and really important stuff as we try to figure out how the structure of the labor market is changing, and jobs and skills in general. Two quick announcements for seminars for next week. We have a special seminar on Tuesday, which is a different time, which is joint with the Institute for Data Systems and Society, IDSS. That is Phil Menzer from Indiana, who will be speaking to a joint seminar. And then on Thursday, the regular IDE seminar on the 21st, Scott Cominers from HBS will be speaking. So look forward to seeing you all at both of these, and you will see announcements and links following up shortly. So thanks again, Dan. Really, really interesting.
Thanks, everyone.
See you all next week. Very cool work.